Morning. It's a bright Saturday morning. I know we all have other plans, but we've stipulated this time for this class, and I'm sure we are not going to end this class and regret joining. So let's have a quick survey. Let's have a quick survey, everybody. Tell us your name and where you're joining us from, real quick. Just tell us your name, where you're joining us from, while we wait for the others. Your name and where you're joining us from. Wisdom from Lagos. Good morning to you. You're welcome. Please let's engage. Let's engage. We all know this is an interactive class. From the beginning to the end, it's interactive. So just in the chat room, your name and where you're joining from. Abiola from Akure, the Sunshine State, you're welcome. Zainab from Lagos, you're welcome. Anastasia from Kenya, you're welcome. Jacob from Accra, you're so welcome. You're so welcome. We're more than that on the call, I guess. Please just few more reactions. Your name and where you're joining us from. Marvin from Nairobi. Yes, you're welcome. You're welcome. Two more and let's kickstart. Two more, two more, two more. Please, your name and where you're joining us from. Adam Singh Bade, I've not heard from you. Honesty, you're frequent in class. Let me hear from you. Where are you joining us from? Ifeanyi, where are you joining us from? Adekunle, where are you joining us from? Your name and where you're joining us from. Real quick, please, real quick. Bade from Lagos. Yes, Bade from Lagos. You're welcome. Adam Singh from Lagos. Okay. So while we have others joining us, let's have a quick recap of what we've learned so far, the first class, the second class, the third class. Today is the fourth, actually. And yeah, if you're joining us for the first time, you are not left behind. The recordings for the first, second, and the third class have been posted on the YouTube page. And if you need the course materials, you can request for them on the Honesty from Benin. Yeah, thank you, thank you, thank you. Adekule from Lagos, you're welcome also. As I was saying, if you're joining for the first time, the recordings for the class have been posted on the YouTube. Before the end of the class, you get the link in the chat room. And other materials are posted only on the Telegram group. Only on the Telegram group. So if you're not there yet, before the end of this class, the link will be posted in the chat room. You have to do well to click the link and join us on Telegram. Materials, questions, exercises, assignments will all be posted only on Telegram. Please take note of that. Before we go ahead for today's class, let's have a quick, like I said, let's have a quick recap of what we've learned so far. We have people that have been frequent in the first, second, and the third class. So let's do something real quick. If you were in the first class, please, can you just do well to remind me of the topic for the first class and just a brief, maybe just a brief short text on what you learned, the topic and what you learned from the first class. If you're in the first class, please just do that. Just one or two people, I'm good. We'll move on. In the chat room, I'm waiting. Honesty, Adekunle, Bade, Jacob, Marvin, you're always frequent. Anastasia, you're always frequent. So please just tell me the topic for the first class and what you learned briefly. Our trainer is there with us and is waiting. So let's do that real fast. Computer science, okay, yeah. Computer science, okay. one more person that was in the first class. What did you, what was the topic? And just give me a brief of what you learned. If it's too long to type, you can just ask to, you can just raise your hand. I will mute you for a few minutes or a few seconds. Just tell us something. Just brief us through what we learned. Data flow chart. Data flow chart was that the first class? Okay, okay. So according to what I have here and what we went through, if you need to speak, please just, you can raise your hand. I'll unmute you. Introduction to computer science. Yes. If you still want us, if you still want to take us through what you learned, we can have a moment for that. We have few minutes, just few minutes for this. If we're just going to keep going, keep teaching, teaching, and not go through what we've learned, I'm not sure we have a good class there. I'm not sure we are having anything good. So if you want to speak, please let us know. We went through introduction to computer science in the first class. What is computer? We went through data science, computational science, information science, and we went through the impact of computer on every aspect of life, in finance, in architecture, in everything. Everything you do right now is computerized. No matter where you sell your business, everything is computerized right now. Hardware, software, blah, blah, blah. And for the second class, we went through computational thinking and design reusability. You can correct me if I'm wrong. So we went through logical thinking, pattern recognition, went through algorithm, and I think we did flowchart too. So if you have anything to say, please don't forget, raise your hand, I will unmute you. And the third class, we went through data structure. I think that was the last class. Yes, if I'm correct. Data structure and algorithm. Also, we went through OWASP. That is Open Web Application Security Project. So last class, it was Mr. Jonathan. Yes, he took us through data representation, process automation. We used tools like draw.io. We used Jupyter for Python coding. And I remember he talked about Google Colab, which is not an effective tool if you are dealing with much data. I hope we all remember that. Also, OWASP, we went through the OWASP, we have the top 10, OWASP top 10. So last week we went through the first one, which is broken access controls. Yes, if I was right. If I'm right, you can correct me if I'm wrong. We went through access controls in IT system, Bob Suits, which is a tool for penetration testing. When you build your software, you have to ensure your software security is intact. So without wasting much of our time, we'll be continuing from where we stopped last week on data structure and algorithm. And on the cybersecurity side, we will be going through cryptographic failures. That is number 2 on the OWASP top 10. I know Mr. Jonathan is ready. I'm so ready to fill us with knowledge today. And I hope we are all joining with our computer, our PC, our laptop, whatever we are going to use to code, because you cannot code effectively on your phones. So please, if you're yet to put that on, make sure your PC is ready. If you're joining with your phone, make sure you have your laptop. If you're joining with your phone, make sure you have your computer. And it is going to be very, very interactive, very, very knowledge. It's a knowledge field section. So um, without wasting much of our time anymore, Mr. Jonathan, can you take us through? You have the floor, please, Mr. Jonathan George.
All right. Good morning, everyone. Good morning. Happy Saturday again. It's nice to be here with you. Hope everyone had a wonderful week. This past week, I'm going to call a couple of persons just to interact. Good morning, Adekunle. Good morning, Nancy. Good morning, Marvin. Good morning, Abiola. I think Abiola interacted with me very well last weekend. I hope your week was fine. Good morning, Anastasia. Good morning, Adamson Wisdom. I hope everyone is doing good. Who wants to have a go, please? If you can, unmute your mic and have a go at what you remember we covered on algorithms last Saturday. Very briefly, very briefly, 2 minutes. Anyone who wants to have a go on what he or she remembers with regards to computer algorithms and data structures? Very quickly. Hello, good morning. Am I audible, please?
Yes, we can hear you, Mr. Jonathan.
Okay. Uh, hello, Honesty. Good morning. Anastasia, good morning. Anyone remembers what we covered on computer algorithms last week? Okay. Think before we continue, I need to hear good morning back so that I know that, we're interacting with each other. That's not a one-way street. At least one person should unmute and just say good morning back. Good morning, everyone. Let's interact, please. Good morning, good morning, good morning. Hi, Timmy, please proceed. Thank you.
Okay, last week we learned about algorithms, time complexity, linked lists, and like other data structures.
Oh, thank you so much, Timmy. Thank you. Wonderful. Thank you. At least I know that uh, I have, even if it's one person that's interacting with me, that's fine by me. Thank you so much, Timmy, once again. For persons who do not want to speak, please feel free to put your contributions in the group chat, even if they have questions, and draw my attention when needed. So without wasting any more time, today we're going to continue from where we stopped: algorithm design and discovery. Now, our introduction to data structures last week focused primarily on representing complex data. However, computer scientists are also interested in designing algorithms for solving a wider variety of problems beyond storing and retrieving data. Now, that will take us, with time goes on, to things like data modeling and artificial intelligence modeling for programming purposes on AI. Now, for example, they may want to plan a route between a start location and an end location on a map. Although every real-world problem is unique, computer scientists can use a general set of principles to design solutions without needing to develop new algorithms from the scratch. Again, data modeling, which we would cover today. Now, just like how many data structures can represent the same abstract data type, many different solutions exist to solve the same problem. An algorithm is a sequence of precise instructions that takes any input and computes the corresponding output, while algorithmic problem solving refers to a particular set of approaches and methods for designing algorithms that draws on computers' historical connections to the study of mathematical problem solving. Early computer scientists were influenced by mathematical formalism and mathematical problem solving. Now, the book, 1945, How to Solve It, outlines a process for solving problems that begin with a formal understanding of the problem and ends with a solution for the problem. Now, a vivid example for this would be, again, without using without using too much cliche, but in the absence of any other word, would be data modeling, where if you want to, for example, I want to create a structure. Now I want to create, structure is not the word, pardon me. I want to create a cognitive or conscious object or conscious machine, as the case may be, that continuously, without necessarily relying on my continuous programming or my continuous instruction to it, is able to decipher how to manage my business in my absence. So what do? I take a set of data inputs. Those inputs called a model or a real life representation of what I want the machine to understand as far as my business is concerned. Those set of models could include, for example, I might give it data inputs on historical data for my last profit made in the business, historical data for how I handled or how I handle periodically the maintenance of my facility. I might give it historical data on how I handle my financial records for the business. I might give it historical data on how I handle relationship with external regulators, including tax regulators, government regulators, and the likes. I might give it historical data on how to handle legal proceedings for the business. And then I give it what is called a guideline or a set of instructions that guide and regulate how the data I have imputed into that machine or computer, as the case may be, interacts with each other. And so I wanted to put the legal proceedings at the fore of its handling my business. Or in some cases, I may wanted to put the physical security at the fore of handling my business. And so I create a mathematical model which serves as a guideline of instruction that says the what they call it now, the physical security or the legal proceedings of my business take the fore of 70%, while handling relationships, managing relationships within amongst the staff take 30%. Now, it doesn't necessarily work that way. What it does is I would tell it, okay, in order to get the optimal performance for managing my business, the optimal performance would equate to or would be equal to fiscal security, legal proceedings, interaction with external regulators, interaction with clients, as well as interaction with internal staffs. And then I run this algorithm or this model, as the case may be, which the model being the business, the optimization of the business equal to these data sets that I just mentioned. And in the process of the algorithm running the model, it tells you, it brings out an output for you and tells you, okay, this is the, given this set of data and the way they relate, this is the data set or data element that comes at the fore to optimize your business. This is the data set that follows suit to optimize your business. And it programs the machine or the computer, as the case may be, to function on that model. In other words, in my absence, as long as that model has been created, the machine can solve any problem as relates to the optimization, the end goal of optimizing my business. without my continually programming it. Why? Because I have already established a foundation, which is what is called data modeling, for the machine to be able to run on, and also with time for the machine to be able to decipher. And so it's just like a child. If when a child is birthed, you teach this child A, B, C, 1, 2, 3, as the case may be. And then as the child becomes 3 years old, he starts or she starts learning and saying, oh, this is how to, the child has already learned how to walk. This is how to greet people. This is how to speak. This is how to react when I'm corrected. By the time the child reaches 7, he or she starts deciphering other things for himself. And with the input data that has been put into that child, the child can then start forming or having a mind of his own. And so that's just the same way data modeling works as far as machines are concerned. We'll visit that as time goes on later today.
Mr. Jonathan, please, we can hear you clearly. And please, can you put your slide on presentation mode, please? We can hear you clearly too.
Mode. Okay. Can you hear me well now? Hello, am I audible enough now, please?
Just a little bit more. I think maybe it's your internet. Just a little bit more audible, please.
Okay. Can you hear me very well now?
Yes, you're good now. You're good.
Okay. Now, as an algorithm's input size is always finite, finding a solution to an algorithm, pardon me, please. Now, finding a solution to an algorithmic problem can always be accomplished by exhaustive search. Therefore, the goal of algorithmic problem solving, as opposed to mathematical problem solving, is to find an efficient solution, either in terms of execution time, number of computer instructions, or space used being computer memory size. Now, consequently, the study of algorithmic problem solving emphasizes the formal problem or task with specific input data and output data corresponding to each input. There are many other ways to solve problems with computers, but this mathematical approach remains the dominant approach in the field. Again, the relationship between input data and output data has to do with data modeling as far as artificial intelligence programming is concerned. Again, I would expatiate on that as the today's program proceeds. Now, there are many other ways of solving problems with computers, but these well-known problems in computer science that we'll explore later in this chapter. A data structure problem is a computational problem involving the storage and retrieval of elements for implementing abstract data types such as lists, sets, maps, priority queues as well. Now, who amongst us wants to have a go remembering what lists and sets are, or the differences between lists and sets as we discussed last week? Anybody? I think I'll call names from the sorry, I'm trying to all right, got your names. I think I'll call names from the all right. Timmy has spoken today. Hi, David. Hello, David. Are you here? Hello, hello, hello.
Hello. Hello,
Yeah.
Jonathan George. Yeah.
Good morning, brother. Do you
Good
want to have
morning.
a go? Yes. Do you want to have a go at what you remember from lists and sets for last week? Or even if it's not from last week, anything from memory on lists and sets and the difference between the two. If you do
I
not
don't
have
remember.
anything, that's
Yeah.
okay.
Sorry, I actually joined the class late. Yeah.
That's very fine.
Yeah.
Oh, no, no, no. That's very, very fine, brother. Please, if I'm in sport or anything like that, we're just trying to uh make it a two-way street, as the case may be,
Sure.
right?
Sure. Yeah.
Yes,
Sure.
definitely. All right.
Yeah.
So thank you very much. So let's continue. Let me return to my slide. Just a second, please. Okay, so algorithms input size. Right, I think have taken that already. A data structure problem is a computational problem involving the storage and retrieval of elements for implementing abstract data types such as lists, sets, maps, and priority queues. And these include the search or the problem of retrieving a target element from a collection of elements in a data set, sorting or the problem of rearranging elements into a logical order. And by that, we explained last week, sorting includes, if you want to, for alphabetical orders, you're having A to Z in an orderly manner, in an ascending manner or a descending manner, as the case may be. And for numerical values or elements, you're having 1 to infinity or -1 to minus infinity, as the case may be, again, in an ascending or a descending order. That's for sorting. All right. Now, hashing, or the problem of assigning a meaningful integer index for each object. Again, we discussed last week and said, given a data set with let's assume 4 or 5 elements, where the first element is 1, 2, 3, 4, 5 in ascending order. If you're going to interact with this data set, or if I'm going to interact with the data set, carrying out things like data retrieval and finding elements within that data set, I cannot, while coding for it, I cannot just walk into the data set. I mean, a data set, when you're talking about, what's the best word to use right now? When we're talking about objects, a data set is kind of abstract, right? We cannot touch it, right? In computational parlance, we cannot touch it. We can only see it. Now, if you're giving a computer an instruction and say, okay, go and find this element within the data set, you have to be able to tell it where to find the element within the data set, right? And so to be able to describe the location within that data set, there has to be things like location points, right? Now, the indexes or the integer index, as the case may be, serve as what can be simplified as location points within the data set. And so in a data set, numerical data set of 1, 2, 3, 4, 5, ascending towards infinity, you're going to have the beginning, the first integer index of any data set always starts from 0. And so you're going to have the index start from 0. So 1 will be represented by index 0, 2 will be represented by index 1, 3 will be represented by index 2, and so on and so forth. Now, if you're starting the indexing from the end of the data set, or the last element in the data set, you're going to have the last element -1. Yes, if I'm correct, I think my memory serves me right. The last element will be -1, and -2, -3, -4, like that. And so that's how integer index work for data sets. Now, a graph problem is a computational, if there's time, I'm going to show practical examples for that if there's time. By the time we finish covering the slides, I'm going to show practical examples for that with codes on Python. Now, a graph problem is a computer. Now, this includes traversal, or the problem of exploring all the vertices in a graph tree is the problem of finding a lowest point to each other within the graph. First way to get from one point to another within the graph. And so you find the real-world applications for this again include applications with things like Google Maps, within a certain location and within a fixed time, or given a fixed amount of resources, or well, map changed when it comes to computer programming. They have their differences though, but they can be applied interchangeably when it comes to programming. And so in certain ways, if you're trying to, the map can be programmed in such a way that, right, if you're using minimum spanning tree, if, for example, I'm trying to find what's the shortest route from where I am at the moment in Lagos to a random location, say Ibadan. In the circumstance, assuming I do not have any idea on how to get to Ibadan, and then I put in the location of Ibadan, and then I tell the map, let's assume the map is, what's the word now? Automated is not the word. Let's assume the map is something I can interact with verbally, right? And I tell the map, please give me the shortest possible route to get to Ibadan from where I am in Lagos. What the map uses is what's called a minimum spanning tree algorithm, right? And that comes with the programming of the software, as the case may be, right? Now, a string problem is a computational problem involving text or information. Examples include matching, or the problem of searching for a text pattern within the document, compression, or the problem of representing information using less data storage, cryptography, which we are going to look at later today in the OWASP top 10 session, or the problem of masking to make it, I'm trying not to use the word unintelligible right now, to make it hard to decipher, right? That's the most simple way to put it, to make it hard to decrypt or hard to decipher, or hard to tell what is within such text, right? And so those are the problems associated with string computational data sets. Last week, we looked at practical examples of string computational data sets, and we're going to be revisiting that today again, if there's time, using the Python Jupyter notebook, if there's time after covering the slides. Now, to the problem of modeling, which is part of the things we looked at the very beginning of today, data modeling. Computer scientists focus on defining a problem model, often simply called a model, which is a simplified abstract representation of more complex real-world problems. They apply the algorithmic problem-solving process mentioned previously to design algorithms when defining models. Now, algorithms model phenomena in the same way that data structures implement abstract data types, such as lists, sets, maps, priority queues, and graphs. But unlike abstract data types, models are not necessarily purely abstract or mathematical concepts. And so models are often linked to humans and social phenomena. A medical system might want to decide which drugs to administer to patients so that the algorithm designer might decide to model patients as a complex data type consisting of age, sex, weight, or other physical characteristics. Because models represent abstractions or simplifications of real phenomena, a model emphasizes some details over others. Please kindly give me 20 to 30 seconds. I want to discuss this in detail. Right. Hello. Any questions thus far, please? Hello. The silence is deafening and it's making me scared. Can anyone interact with me, please? I need to know that we're following. I need to know that we are understanding what is being discussed. I need to know if you have any need for more real world examples, please kindly let me know.
Please, if you'd like to speak, just raise your hand and you'll be unmuted, please, if you need to speak.
Okay. Okay. All right. Okay, that was it says can hardly hear me. That's Adamson wisdom. Okay, Stella says we cannot unmute ourselves. Okay, hi Stella, that's fine. I understand. Please, okay, one person has his hand up. Okay, no. All right, Stella, I understand that's fine, but please, if you have any question, feel free to put it on the group chat and I'll be happy to interact with you. Okay, my signal goes on and off. Atemi says the same thing. Please, I deeply apologize. I am trying not to switch my networks again like last week so that it doesn't log me off. But please, anytime it's my signal breaks, kindly call my attention back to it so that I can revisit anything I've said that wasn't very clear. All right. Thank you. So back to computer modeling, right? As we were discussing right now.
Sorry, Mr. Jonathan. Honestly, you're unmuted.
Yes.
You want to speak?
Yes, good afternoon, sir.
Good afternoon, brother.
Sir, please, we need more rework examples too.
Definitely.
To really
So,
get what you are explaining, sir.
okay, all right, definitely. So last week I did a couple of practicals for you using Python, but I'm trying as much as possible today to manage time, right? So I would try as much as possible to manage the information that I have to pass to you. And where there's time and ample opportunity, I definitely would give practicals using Python for you, so that nothing is left behind, right? Is that fine by you? Okay. Here's what I can do, right? Let me share my so that I'm not let me share my please just a second. Let me put on some practicals. Let me undertake a few practicals so that I'm not just traveling on my own on this journey. Okay, all right. All right, so now we're at the stage of data modeling, right? Now I'm just briefly going to go over the. I'm briefly going to go over the string data type right now. Okay, so text equals to I have a come out with correct. I have a drive for okay, I have a drive for success, or let me not use I, let me say we, all right, so that it's more inclusive. So we have a drive for, all right. We have a drive for success, right? Print
Sorry, please, if you
text.
have any issues using the Jupyter, please just let us know in the chat room. If you have any issues getting on Jupyter, please let us know in the chat room.
Okay, so well, this is not the way I want to put it. So what I'm going to do is I'm making an error with my code. Anyway, this is the idea behind a string text. And so what I'm supposed to do, there's supposed to be space here, and that's where I'm making an error. That can easily be fixed. Part of the things that works when it comes to programming, right, is that at some point you're definitely going to make errors. And so the the skill of a good programmer is knowing how to troubleshoot your errors. Now, before the advent of AI, there was something we used to use. I'm trying to remember the name now. This there was something we used to use. There was a site or used to troubleshoot things like this. But this is an error. Let me just quickly troubleshoot it and uh so okay. Okay. Uh, what am I doing? Okay. Um, space. All right. Let me just check. So we plus space. No. I'm not space. So E plus space plus half plus space plus A plus space plus drive plus no, this is wrong. All right. Plus space plus 4 plus space plus let me see. All right. All right, so so that we don't waste so much time here. This for now we can always let me check if I will see the site and the site for troubleshooting. Um, the site we used to use. No. All right, let me not
Okay,
waste
sir.
so much time, right? I'm just going
Yes,
to
sir.
quickly. Yeah, is someone speaking to me, please?
Yes, yes, I am. So please,
Oh,
for the
please.
side you were coding, can we also put spaces inside the quotes, like after each word, like as an alternative to putting an empty string?
No. So what I'm going to do with that is I'm going to troubleshoot it now on what they call it, ChatGPT for you, so that you just see it once and for all. All right, so I'm trying to see where I definitely made an error somewhere, right? Let me quickly look at that again. I'm not going to waste so much time on this, but let me just quickly look at that again.
Mr. Jonathan, please, can you check the chat room? I think Josiah has.
A question for me. All right,
Yes.
I will definitely go there now. Okay, so I also put in spaces in between my this thing. All right, so um you can see the way to make the code correct. You give the spaces. So yes, we're correct on the clause, but here there was supposed to be a space between the parentheses. Yes, between the parentheses there was supposed to be space, and I wasn't putting space, right? So yeah, that was the cause of the problem. So we have a drive for success. Now you can see it. Now this is what's called a string text, and this is just a simple format. Now they're just as with please, I'm coming to the chat box now, but let me just on this now. Just as they are, what they call it now, they are procedures is not the word. They are processes, right? Or yes, they are processes with the arithmetical data or the integer type data, where you have the subtraction, the addition, the multiplication. You also have such as well with string text. The details of that we can't go into today because it's a whole course on its own. It's called natural language programming rather, NLP, right? And that's it takes hours to go around that. So we'll revisit that any other time when we have the opportunity to do so. Let me just go to it said Josiah, right? I don't have it installed. Okay, so Josiah, uh you just go to just a second, please. we put this up last week, but I'm going to do it for you again very quickly. You go to okay, so you can go to your okay. Let me use this. Please, if you're looking at my screen, Josiah, if you can see my screen, you would see what I'm doing now. You can just, I will put the link for you on the chat box now, but I just want to get the, right, because I know how to download it, but I do not have the step-by-step instruction from my head. So you can still hear me. I don't know, the network is very slow. If you see that, let's not spend so much time on that right now. All right, so provide, okay, skip registration. I think that should be the right thing. Yes, so I'm going to put it for you, and then you click download, right? Am I correct? Yes, yes, yes. And so let me just show you again. You type, let me give you this link so that it just make your work easier for you. Right, so that's the download link for Anaconda. And once you're done with downloading Anaconda, Anaconda is like an umbrella software for Python as well as other. Let me just show you. Let me also share that as well. Then we quickly return to the class so that we need to round off, cover everything today. And let's do that successfully. So this is Anaconda. Once you successfully download Anaconda, then you come to definitely you open the software and then you see Python Jupyter. Now it's showing launch here because I've already installed it, right? You can see what it will show if I've not installed it. It will show me install. Now, in the event where it shows you install, please go ahead and click install so that it can install. And once it's done, then you can click things like launch. And yes, you can now see this is the way it would open for you. It would run on your local machine. And yes, you go to new, you click new, and you click Python 3. And it opens the terminal or the notebook for you as it has done for me right now. And then you can impute your codes, and learning how to use the notebook would be, that's a whole different class altogether, right? So let me just quickly return to what we have today, right? Now, all right, I think I've covered this. A string has also covered this, right? Computer scientists focus on defining a problem model, often called or simply called a model, which is a simplified abstract representation of a more complex real-world problem. They apply the algorithmic problem-solving process mentioned previously to design algorithms when defining models. Algorithm model phenomena in the same way that data structures implement abstract data types such as lists, sets, maps, priority queues, and graphs. But unlike abstract data types, models are not necessarily purely abstract or mathematical concepts. Now, models
Sorry,
are
Mr. Jonathan, we can't see your screen.
really.
Yes, sir.
Okay, it's showing me here that I'm sharing. Yeah, but let me just, maybe I unshare and reshare. I don't know what could be wrong. Just unshare and reshare. Can you see my screen now, please?
Yes, we can. Yes.
Hello. Okay.
Yes, we
All
can.
right. All right. All right. I can find my cursor. All right. All right. So the medical system might want to decide which drugs to administer to which patient. So the algorithm designer might decide to model patients as a complex data type consisting of age, sex, weight, or physical characteristics. Now, again, data modeling has to do with using the data input type or data input elements to determine what the output would look like. And so if I want my output to determine in the event now where, for example, we are discussing the medical field, I want my output to determine the health status of an individual. And I take my data input element to include things like weight size, or weight rather, weight, body mass index. I don't know, remember if that's equal to weight, but body mass index, weight, maybe blood type, depending on the relevance. Now, the key to data modeling is the fact that the data imputed into the algorithm or the data imputed into the machine or the computer, as the case may be, must have a high degree of relevance to the output that you want to be able to produce. And so if I'm trying to produce the health status of an individual, it's completely wrong or inappropriate for me to impute a data type that has to do with shoe size. Now, shoe size has no relevance in regards to or with regards to the health status of an individual. And so in building a data model for machine programming, you have to ensure that the data imputed has a high degree of relevance to the data you want to, or to the output you want to achieve from such program, as the case may be. So if an algorithm is a solution to a problem, then the model is the frame through which the algorithm designer defines the rules and potential outcomes. Again, going back to the relevance between the data input and the output that you want to achieve. Without models, algorithm designers will with the infinite complexity and richness of the world. That is, in the event where the data imputed has no relevance to what you want to achieve, you're just going to be picking any data sets that you see. And so without models, algorithm designers will struggle with the infinite complexity and richness of the world. Imagine, for example, designing a medical system that models patients at the level of individual atoms. This model offers a detailed representation of each patient in the most physical or literal sense. But this model is impractical because we do not know how particular configurations and collections of atoms contribute to a person's overall health. Again, the relevant to the output that you want to achieve. Compared to this atomic scale model, our former model consists of age, sex, weight, and other physical characteristics. It's more practical for designing algorithms, but necessarily involves erasing our individual humanity to draw certain conclusions. In order to design algorithms, we need to be able to focus on relevant information rather than detailed representations of the real world. Again, the degree of relevance between the input data and the output that you want to achieve. Further, computer science requires a philosophical mind to aid in problem solving. According to Brian, philosopher and cognitive computer scientist, though this is not the place of metaphysics, it would be too much to say, it will not be too much to say rather, that every act of conceptualization, analysis, or categorization does a certain amount of violence to its subject matter in order to get at the underlying regularities that group things together. Without performing this act of modeling, there would be too many details to wade through to create a useful algorithm. Again, taking us back to the degree of relevance between the input data and the output that wants to be achieved. The relationship between algorithms, the software they empower, and the social outcomes they produce is currently the center of contested social and political debate. For example, all media platforms, including popular ones like Netflix, use some level of targeted advertising based on user preference in order to recommend specific movies or shows to their users. And so if I want to recommend a movie or a show or music, as the case may be, to you, what I will be looking out for is what's your past preference within the last 2 years? What have you watched? What has your music history been like in the past 2 years on social media or on social applications or music applications? And so I look at your music history. I also look at things like, I also harvest data on things like what you discuss with your friends on social media that has to do with your musical preference or your entertainment preference, as the case may be. And then I collect that data together. Say for the past 1 year might not be sufficient. Again, when it comes to data modeling, size is important. And so if I want to arrive at your preference for your most preferred music type, on the next music I will suggest to you, say, for example, YouTube. How many of us remember the suggestions that YouTube gives us? If we go to YouTube, we finish watching a video, YouTube recommends another one to us and say, they think we'll like this. Why do they know what our preferences or choices would be? They do this because they have access to our historical data, both on YouTube. They also have access to our historical data, both on Google. If many of us would remember and know, the owners of Google equally are the owners of YouTube via Alphabet Inc. And so they have access to your historical data on Google, they have access to your historical data on YouTube, and then they have access to your historical data on certain other social media platforms that they are affiliated with. And they collect all this data together and run it through an algorithm. And the algorithm looks at it and says, okay, in the past 2 years, this person has been listening to rhythm and blues. In the past 2 years, this person has been watching political discussions since 2023. Okay, so we think that the next video or the next speech that this person wants to listen to will be a speech by President Tinubu, or be a speech by President Trump, or be a speech by President Macron, and so on and so forth. Right? And so data input, the relevance of data input, the size of data input, they also look at, if I want to get the most optimal output from that data relevance, I would have to look at, okay, what has this target person been viewing for the past 3-4 years? Now, that would give me much more optimal results compared to if I'm looking at what has this person been watching or listening to for the past 6 months, right? Because with size comes variety, and with variety comes accuracy when it comes to data modeling and data processing as far as programming for machines are concerned. Again, with size comes variety, and with variety comes accuracy, so that you do not go into something in machine modeling called overfitting. And so if I train my data set on what a person or an individual or target a target person, as the case may be, has been doing for the past 6 months, my data set would overfit or would over assume its output tied to the past 6 months. But if I train my data algorithm or my data set with regards to what the target has been doing or has been viewing for the past 4 years, 10 years, as the case may be. Now, data set or the program, the machine has the option of picking out of a wide variety of choices and say, okay, this person liked R&B in the last 10 years. But in the last 5 years, we noticed that the person switched to gospel music. And in the last 2 years, we noticed that the person switched to rap music. Oh, this person must be very unstable. Or the person has been very constant with data for the past 10 years. The person has just been listening to only gospel music. This person must be a huge fan of gospel music. Now, in the event where, for example, the target person has been changing their preference for the past 10 years, say from rap to gospel, to rhythm and blues, to reggae. The question will be, with further analysis, what is the pattern of that change? What has spurred that change, right? And so we, as data scientists, we therefore go in to collect more data sets and say, okay, has the person been, what other data set type correlates with the changes that we can observe in the data sets, right? Has the person been, when the person was listening to rap music, was the person employed? When the person switched to rhythm and blues, was the person depressed? When the person switched to gospel music, was the person trying to give praise and adoration to God for getting a new job, right? So we take into the more variety we notice in data patterns and data sets in a given data model used for programming a machine, we take into cognizance the influences or the determinants, as the case may be, the determining variables. There's a word they're called, the determining variables that determine the change or the variety in the data set pattern, right? And so that's that for that explanation. Let me proceed in the meantime. Now, the relationship between algorithms, the software they empower, and the social outcomes they produce is currently the center of contested social and political debate. For example, all media platforms use some level of targeted advertising based on user preference in order to recommend specific movies or shows to their users. Now, users may not want their information to be used in this way, but there must be some degree of compromise. And that's again because the machine must have access to historical data for it to be able to model its thinking, model its creativity, model its prediction. Prediction is the right word. Model its prediction to be able to give the most optimal outcome for the target or the target user or target state, as the case may be. On the one hand, the technical definition of an algorithm is that it represents a complex processes as a sequence of precise instructions operating on data. Now, this definition does not overtly suggest how algorithms encode social outcomes. On the other hand, computer programs are human designed and socially engineered. Algorithm designers simplify complex real-world problems by removing details so that they can be modeled as computational problems. Because software encodes and automates human ideas with computers, software engineers wield immense power through their algorithms. And this speaks to the fact where, for example, how do I put this down? There's a name for them. It's not big data. It's okay. So let me just use this analogy. How many of us know Silicon Valley? Silicon Valley. Anybody? How many of us know Silicon Valley? Okay, they're the capital of software and computer engineering and design in the world. In the United States, definitely. Now, the fear is that the likes of Facebook, Google, Microsoft, and so on and so forth, Amazon especially, have access to your data. How do they have access to your data? Now, if you go to Amazon, they sell books and movies and some other social products. Now, if you go to Amazon, you buy products from them, you listen or watch movies on their devices or their applications, as the case may be, they take record of your data. And so the data they collect from your operations on their platform become historical data, and they can use that to predict and tell you things about yourself better than you understand yourself. Hence, the saying, he who owns the or holds the data rather in the 21st century wields the power. And so they owning and holding the data of the target individual gives them power to be able to predict the next move of the individual, to be able to predict the thinking of the individual. For example, my going on Google or YouTube, as the case may be, and YouTube telling me they think I'll prefer this video. They think I'll prefer that video. There are times or occasions whereby I'll be on Twitter and I'll be making research or browsing through news on Twitter, and then I'll just come to YouTube, and what I was just reading on Twitter is my next suggestion on YouTube, right? And so for reasons best known to them behind closed doors, many of these social media applications or companies, as the case may be, are affiliated in some ways. And so at some point in time, they collaborate in data sharing and the likes, and it can always pick out algorithms. And so an algorithm that can predict and say, this is my next move, even when I myself do not know what I'm going to do, is a very powerful tool. Now, the individual or the company that holds that algorithm or is in charge of that algorithm is a very powerful individual and wields both social and political power as well as psychological power over me. And so that's just what this speaks to. The software encodes and automates human ideas with computers. Thus, software engineers wield immense power through the algorithms they build and the algorithms by extension which they control. To further complicate the matter, software engineering is often a restrictive and formal discipline. Now, problem modeling is constrained by the model of computation or the rules of the underlying computer that is ultimately responsible for executing the algorithm. Historically, computer science grew from its foundations in mathematics and formal logics, so algorithms were specialized to solve specific problems with a modest model of the underlying phenomena. This approach to algorithm design solves certain types of problems, so long as they can be reasonably reduced to models that operate on a modest number of variables. However, many variables the algorithm designer can keep in mind. In the case of the medical system, the algorithm designer identified certain characteristics as particularly useful for computing a result. And that brings me to something that has escaped my mind thus far, and I'm just refreshed on. So when dealing with a data set, right, we can call the what's the word now? So we can call the elements within the data set elements, right? But when dealing with a data model, we refer to them to the elements as variables. And so the input variables, yes, are called predictive variables, right? And the output variables, let's leave the output variables as output variables for now. I'm trying to remember, there's a professional term, it's escaped my memory, so that's the reason for the pause. There's actually a professional term for it. When I remember, I definitely will revisit it. But there's a name for the output variable, right? And so again, there must be a high degree of relevance between the predictive variables or the input variables or the deterministic variable to the output variable or the output that you want to achieve, right? There are many other problems that defy this approach, particularly tasks that involve subtle and often unconscious use of human sensory and cognitive abilities or faculties. An example of this is facial recognition. If asked to describe how we recognize a particular person's face, an algorithm designer will be challenged to identify specific variables or combinations of variables that correspond to only a single person. The formal logic required to define an algorithm is strict and absolute, whereas our understanding of human faces is defined by many subtle factors that are difficult for anyone to express using formal logic. Now, the search algorithms in computer science, searching is a problem of retrieving a target element from a collection that contains many elements. There are many ways to understand such algorithms depending on the exact context of the problem and the input data. The expected output might differ. For example, suppose we want to find the target term in a dictionary that contains thousands or millions of terms and their associated definitions. If we represent this dictionary as a list, the search algorithm will return the index of each term in the dictionary. Again, taking us back to what I discussed, or what we discussed rather, about indexing, where the first index is always 0, the second is always 1, 2, 3, 4, 5, as the case may be. And then if you're starting from the end of the data set, it starts from -1, -2, as the case may be. Now, if we remember, I said that without indexing, it's going to be difficult to find what you're looking for, or the element or the variable you're looking for within the data set. And the reason being that if you ask me, or I ask you to please help me retrieve my bag, definitely your next question will be, from where? And so I have to give you a location or an index or a point to go and search, right? And even if I'm not able, let's assume I'm not very sure about where exactly it is, and I say, please just help me look around. And then you look around and you bring it. My next question would be to you, where did you find it? And then you have to give me a location or a point or an index and say, I found it in the second row at the left, or I found it at the topmost floor of the second building in the next compound. That's an index, that's the location, that's the point within the data set, right? And it takes us to the next part. All right, let me quickly finish this. Despite these differences in output, the underlying canonical searching algorithm can still follow the same general procedure. The two most well-known canonical search algorithms are known as sequential search and binary search, which are conducted on linear data structures such as array lists. And so we looked at what an array list is practically within the Python Jupyter Notebook last week, where we defined an array list and printed it out. That was last week. So the sequential search from image 7, just you're going to have access to this document, opens the dictionary to the first term. If that happens to be the target, then great, we have found the target. If not, then repeat the process items in the dictionary. Hear me loud and clear. Hello. Hello.
Mr. Jonathan, we are with you.
Hello,
Your network
hello.
was breaking for a bit, but I think it's back now.
Oh, okay. All right.
We are with
Okay.
you. We are with you.
All right. Let me return to the slide, please, very quickly. Okay, now the binary search opens the dictionary to a term in the middle of the dictionary. If that term happens to be the target, then great, we have found the target. In other words, the binary search divides rather the data set into two. We spoke about that last week. Divides the data set into two and looks at if it's an alphabetical, it works, the binary data search actually works only for sorted data or sorted data sets rather. And so if the binary search divides the binary search rather divides the data set into two halves, it checks the target variable, which is the variable it is looking for, against the sorted data set, and checks and says if it's A, it's looking for, definitely A will be in the first half of the data set, right? If once it's sorted, A would definitely be in the first half. Now, if it's Z or Y or Z or W, as the case may be, that would definitely be in the second half of the data set, right? Because it comes in a dictionary when you divide into 26 into two equal halves, definitely XYZ comes in the second half of the data set, right? Now, rather than rely on direct analogy to our human experiences, these two algorithms for the autocomplete feature compose one or more algorithm design patterns to solve the problem. How do we know which approach might be more appropriate for use? One type of analysis is known as algorithm analysis, which studies the outputs produced by an algorithm, as well as how the algorithm produces those outputs. Now, those outputs are then evaluated for correctness, which considers whether the outputs produced by an algorithm matches the expected or desired results across, considered correct only if its computed outputs are consistent with all expected outputs. Otherwise, the algorithm is considered incorrect. Now, although this definition might sound simple, verifying an algorithm for correctness is often quite difficult in practice because algorithms are defined or designed rather to generalize and automate complex processes. The most direct way to verify correctness is to check that the algorithm computes the correct output for every possible input. This is not only computationally difficult, but even potentially impossible to achieve, since some algorithms can accept an infinite range of inputs. Now, verifying the correctness of an algorithm is difficult not only due to generality, but also due to the ambiguity of data. Now, earlier we saw how canonical search algorithms may have different outputs according to the input collection type. What happens if the target term contains special characters or misspellings? Should the algorithm attempt to find the closest match? Now, we'll just quickly skip. Correctness primarily considers consistency between the algorithm and the model, rather than the algorithm and the real world. Our autocomplete model from earlier returned all word completions that matched the incomplete strings of letters. But in practice, output would likely be unusable. A user typing A would see a list of all words starting with the letter A. Now, since our model did not specify how to order the results, the user might get frustrated by the irrelevancy of many of the word completions. Suppose we remedy this issue by defining a relevancy metric. Every time a user completes future auto-completion request, in algorithms of operation, determining relevance in this universalizing way can have undesirable social impacts. Perhaps due to relevancy metrics determined by popular vote at one point, Google search auto-suggestions included ideas like women cannot drive or be bishops, be trusted, or speak in church. By the way, before I continue, happy International Women's Day to all women in this class with us today. We celebrate you, we appreciate you, and we definitely promote women in all walks of life. So happy International Women's Day once again to all women. Participating for the writer of the book, Algorithms of Oppressions, extends further to consider the intersection of social identities such as race and gender as they relate to the outputs of algorithms that support our daily life. As the amount of input data increases, computers often need more time or storage to execute algorithms. This condition is known as complexity, which definitely we'll still cover today, which is based on the degree of computational resource that an algorithm consumes during its execution in relation to the size of the input. More computational time also often means consuming more energy. Designing efficient algorithms is not only of practical value, but also existential value, as computing contributes directly to global warming, definitely via the use of electricity, and resultant climate crisis. Marginalized users of the platform who may be further marginalized by this definition of toxicity. Content moderators who are each reviewing several hundred pieces of the most toxic content for hours every day. Legal teams who want to mitigate government regulations, amongst many others. Now, formal properties of algorithms. Now, beyond analyzing an algorithm by examining its output, computer science by performing an algorithmic analysis, a study of how much it takes to run an algorithm efficiently. If you have access to a runnable program, perhaps the most practical way to perform a runtime analysis is to time exactly how long it takes to run the program with evaluates an algorithm by rate. Experimental analysis is particularly effective for identifying performance or codes that consume unusually large amounts, even though it produces the correct output. In e-commerce, for example, performance bugs that result in slow website responsiveness can lead to millions Hello, hello. Uh, can anyone hear me, please? Hello, hello, hello. Okay, all right. Thank you very much. Okay, let me just quickly share my screen again. I apologize for the network disruption. very quickly, going to share my screen now. All right, so the network logged me off. Make a purchase online via an online Temu, the Temu market space, and the second one is Jumia. Now you log into Jumia, and Jumia is taking runtime to process its algorithm. It's taking exceedingly long time to process output for the inquiries you're making on the platform. And I can't remember which one I just said now. Let's assume the first one I just gave was Jumia. And then the next one, Temu, you log on to Temu and the algorithm processes all your inputs to make purchase very quickly, right? Which of them do you think you would be more attracted to use? Which of them would you shop with? Very quickly, please put it in the chat box. I would continue as you respond in the chat box, right? I'll be expecting your response. Now, while experimental analysis is to use if we do not already have a working program, programming large systems can be expensive and time-consuming. So many organizations want to compare multiple algorithm designs and approaches to identify the most suitable design before implementing the system. Definitely to achieve an optimization of that system. Even with sample programs to represent each algorithm design, we can get different results depending on the processing power, amount of memory available, and other features of the program that is running. And so a profiler is a tool that measures the performance, including runtime and memory usage of a program. Profilers are commonly used to diagnose real-world performance issues by producing graphs of how computational resources are used in the program. An example of this, a real-world example of this, would be this image. And this is strictly for people who are working at the back end. And so if you are a business analyst who is looking to optimize, definitely you are not the one building. What you are just going to be doing is interpreting and say, okay, this is a profiler. What's the best runtime for each algorithm? Which algorithm gives us the best runtime, including the amount of time and the amount of memory used to achieve an efficient result on the platform? Right? Now, one way to measure the efficiency of an algorithm is through time complexity, a formal measure of how much time an algorithm requires during execution as it relates to the size of the problem. In addition to time complexity, computer scientists are also interested in space complexity, the formal measure of how much memory an algorithm requires during its execution as it relates to the size of the problem. Now, both time and space complexity are formal measures of the efficiency of an algorithm as it relates to the size of the problem, particularly when we are working with large amounts of complex data. So you would not want to, as a computer scientist, you would not want an algorithm that takes up 90% of the space or memory on your data storage platforms when you have more programs to run, able to maximize both space for your data storage capacity, as well as maximize time to be able to optimize output efficiently in ways such that the consumers of the data set or the data output are satisfied with the delivery, the amount of time it takes to deliver output to they themselves, the consumers. Again, you want to maximize time, you want to maximize space for your data storage capacity, so that one program, the algorithm for one program is not taking up the amount of space that you also want to maximize time again, so that, or in such a way that the consumer, the final consumer of the product, or the final consumer of the data at the output end is satisfied with the amount of time it takes to deliver the output to he or she, or they themselves, the consumers. And so what you are looking for the consumer side, for the time part of the complexity of data processing and programming, the less time it takes for an algorithm to run and process data, the more optimal that algorithm is to the consumer. And if you remember, anything that has to do with business, the consumer is always right. And so the more optimal the time and the algorithm is to the consumer's needs, the more optimal that algorithm is definitely to your business, right? So let's quickly move on from there. Remember the question I asked, which website would you be attracted to? Please, I need response in the chat room. I may not be able to go through all of them now, but definitely we would have some time to interact. I want to cover the course as much as possible. We'd have time to interact definitely before the program rounds up today, but please, I need a response to that question. Given Jumia and Konga, let's use Jumia and Konga. Jumia and Konga, Jumia is wasting time to the algorithm for Jumia is wasting time to respond to your needs. The algorithm for, again, I've forgotten which one I just called first. Let's take it again. The algorithm for Jumia is wasting time to respond to your needs, and the algorithm for Konga is responding to your needs exceedingly fast and efficiently. Jumia is wasting time. Konga is not wasting time. Which would you shop with, right? It has to do with time complexity of algorithms, right? The space complexity, again, that has to do with your data storage capacity. In the event where you have to manage, you definitely have to manage your data storage at all times, because data storage is not infinite, right? And even if it's infinite, the resource to manage it is not infinite. It's never infinite. And so if you're managing your resource, you definitely have to manage your data storage capacity. Now, the analysis is not quite complete. We might have to find a target word early in the list for, let me return here. The next task is to number the model of steps needed to execute the algorithm while considering its potential behavior on all possible inputs. And so as much as you want to maximize time and space, you also want to ensure that the algorithm is correct. You also want to ensure that the algorithm is not, quote unquote, misfiring. The algorithm is not giving a wrong output to you, right? And so you do not put time and space ahead of output. There must be a balance amongst all three. How does the runtime change as the size of the problem increases? We can see that the repeat part of our description is affected by the number of words in the list. More words can potentially lead to more repetitions. And so the algorithm needs to go through, in the case of a string data set, an algorithm is trying to process, for example, now, I want to make calculations, and the calculation is 2 examples in my head. And this example that I'm going to give using my own head is the same way computer works. And so you tell me, let's assume you are my teacher today. And then you tell me and say, Jonathan George, give me the answer for 1 + 1. Within a nanosecond, I can tell you off the top of my head, it's 2. Then you now say, Jonathan George, give me the answer for 1 + 1 divided by 2 divided by 3 + 5 divided by 6 multiplied by 10. Definitely, I would slow down, right? Because I have to process, I have to run through the data multiple times before I can give you an output or a response, right? It's the same way an algorithm works. And so the greater the size of the data set, the more complex the data set in question, the more the algorithm has to run through that data set multiple times to ensure that it covers the nitty-gritty of the data set and to ensure that it is able to go through the operations that have been demanded of it. And so you can find in the second operation, you're asking me 1 + 1 divided by 2 multiplied by 3 divided by 6 multiplied by 5 multiplied by 10 hash by this. I have to run through all those operations multiple times before I can give you an answer. And so I will not be as efficient in that as I am in telling you the answer for 1 + 1 = 2. It's the same thing with the efficiency of an algorithm as the size of the data set increases, right? And you'd find that as a data scientist or computer engineer, these things are much more important when it comes to optimal programming, far more than the coding aspect. And so off the top of your head, you can cram codes and know all the codes, but if you are not good, if you do not know the decisions to make, the choices to make as far as algorithms are concerned, the choices to make as far as memory partitioning is concerned, the choices to make as far as optimization of data set is concerned, the choices to make as far as the right variables are concerned, then you definitely are not going to be able to perform well, right? And so in data modeling, computer programming, as far as data modeling is concerned, you find that the coding is just maybe 20%, contributes maybe 20%. The remaining 80% has to do with your data set, the data set in question, the variables within those data sets, how the variables are modeled, the relevancy of the variables to the modeling, the type of algorithm you're using, the partitioning of the space, all those carry the remaining 80%. If those are not properly managed, your coding or your programming comes to 0, right? And so let's move on. Now, we might find that the target word early in the list, even if the list is very large. Although we define the size of the problem as the number of words in the list, the size of the problem does not account for the exact words and word ordering in the list. Computer scientists say that this algorithm has a best case situation when the word can be found at the beginning of the list. We looked at this practically last weekend, right? When I showed different types of searching. That will be at the topmost part of the. We'll revisit that later if there's still time. Now, computer scientists say one way to account for the variation in runtime is via case analysis, which is based on factors other than the size of the problem. Finally, we can formalize our description using either precise English or a special mathematical notation called big zero notation. Now, a practical example of this would be, like I recalled citing last week. A practical example would be, now I have my room, or anybody within this class has their room full of materials, junks, and the place is scattered. Let me use myself as an example. Let's assume my room is scattered, filled with junks, and I'm looking for my laptop. And I just open the door to my room, and the laptop is the first thing I see. I won't waste time in finding it, right? Very current rubbish. And my laptop is within that rubbish. And I open the door to my room, and my laptop is not the first thing, but is muddled up within the junks scattered in my room. It will take me a much more amount of time to find my laptop, right? Correct. That's exactly what is being described here. When they say, one way to account for the variation in runtime for an algorithm in finding or deciphering an output variable efficiently is via case analysis, which is based on factors other than the size of the problem. In the practical example, factors other than the size of the junk in my room, and those factors would be location, of the target variable, or location of, yes, the target variable to be processed by the algorithm, right? Finally, we can formalize our description using either English. Okay, we've looked at that. In the best case situation, where the target word is at the start of the list, sequential search takes just one repetition to find the word in the list. Again, that's the example I just gave right now, finding my laptop once I open my door, even amongst chunk of scattered items within the room. Why? Because it's the first item once I open my door. In the worst case situation, when the target word is either at the end of the list, right? Now back to the practical example where my laptop is at the end of the rubbish or at the end of the junk within my room that is scattered. Let's assume my room is so terribly scattered and my laptop is at the end of that junk, right? It's going to definitely take me time to find my laptop, all right? You'd agree with me on that. Am I correct? And the reason being that I'll have to go through all that junk. I have to separate this A from B. I have to separate junk A from junk B just so that I can get to my laptop. And that's what's being discussed here, right? Big O notation or big zero notation for orders of growth. I showed practical examples of this last week, and I can revisit that again in the last 1 hour of this course. The 1970s, computer scientists applied asymptotic notation growth. We can use big zero notation to describe the time complexity of the sequential search algorithm. In general, we say a function fn is in the class of this if the function n tends to infinity. Now, in the best case, the order of growth of sequential order is in 0, 1. The constant order of growth is described in big zero notation as while they, okay, so for this, I'm going to recap the practical example I did on that last week, where we said the types of algorithmic runtime. We have the constant, we have the logarithmic, we have the linear. I think that should still be displayed here, if I'm correct. I didn't close it. So let me just see. No, this is not it. All right, so this is it. This was from last week. Yes, it's even still showing 7 days ago. Algorithmic complexity. So we have the constant time complexity where the execution does not change with input size. And it occurs, for example, if you're looking for, like the practical example I just gave right now, if I'm looking for the first item within an item of junk, you know, that's a practical example for that. Let me check the, sorry, please. Okay, my screen sharing is paused, all right. Conga. All right, my screen is blocked. I apologize, please. I'm going to, I know why. It's because I opened the chat box. All right, so Conga, definitely people said they will go for Conga, which is correct. Thank you for everybody that contributed. And so the linear time complexity is the time complexity where execution grows proportionally with the input size. And so if input size increases by 1, the execution time for the algorithm increases with an equal proportion to 1, right? An equal computing proportion to 1. Quadratic time complexity is one whereby the execution time grows exponentially as input increases, right? Is you can use that for nested pairs or bubble sort.
Sorry, Mr. Jonathan.
Yes, please.
Okay, please. I think if you put your slide on presentation mode, it's not going to get blocked. And Just want to call your attention. We'll be going on break by 12, so it's like 5 minutes before the break. Thank you.
Okay. Okay. The reason I'm not, I refrain from putting my slide on presentation mode is so that I can know like page, the number of slides at, so that I can be able to keep track of my pace and time, so that I can be able to manage my time properly. All right. So, but maybe what I can do is, I'll find a way to manage it. I'll find a way to manage it properly. All right. And so that's that on algorithmic time consumption and algorithmic time management, right? Now, algorithmic paradigms, algorithmic design patterns are solutions to well-known computing problems. Now, we'll survey these design patterns below. As it turns out, many of these algorithm design patterns share similarities in their approaches to solving problems. Here we'll introduce the algorithmic paradigm, which is the most common concept and idea behind algorithm design patterns. We have the divide and conquer algorithm, which is an algorithmic paradigm that breaks down a problem into smaller sub-problems, which is it divides it and solves each sub-problem, and then combines the results of each sub-problem to form the overall solution. In doing this, it's able to manage time faster. And so I'll give another practical example again, take it back to the scenario of my scattered room, right? The hypothetical scenario of my scattered room where my items are scattered and I'm looking for my laptop. And so one of the best ways of solving this or managing the situation would be to divide the junk into, instead of just shuffling through the junk, through the huge pile of junk, divide the junk into sections, or if it's a data set, as the case may be, divide the data set into sections and go through it section by section rather. I go through it section by section and okay, I see that, oh, my computer is not in this section A. All right, I leave section A. My computer is not in section B. I leave section B. My computer is in section C. Very good. Now, if I'm looking for the charger, I now say, okay, I didn't find the charger in section A, section B. I didn't find it in section C. It's either in section D or section E. I go through it and I see that my charge to search section C, section E rather, which is the last section, right? And so I join the data sets back together. And I take my charger and my laptop, which is the output variable that the algorithm is supposed to bring. And I take it and go the data set into sub-problems or sub-categories, solving each category one after the other, and then merging the data set back together. But this time, merging it after I have brought out my output variable, right? And so that's that for divide and conquer algorithms, right? Binary search, we've looked at it before. It makes a single recursive call on the remaining half of the list as part of the conquer step. But other divide and conquer algorithms make multiple recursive calls to solve their problems. Now, again, the easiest example I would give to this would be the dictionary, right? So I want to, okay, let me read this out very quickly. After this, we're going to go on the break. I'm not going, it's 11:59 on my own clock. So after this binary search, we'll go on the break. And when we come back, we'll look at brute force algorithms, greedy algorithms, and from there we'll be winding down, right? So binary search divides, it works, like I said, for sorted data sets where you can tell by dividing the data set into two, you can tell where the given target variable would lay. So you're trying to process a target variable of or find an output variable of 2, right? You divide your data set, which is a dictionary of numbers of 1 to 10, into 2 equal halves, 1 to 5, 6 to 10. Where would the number 2 dwell? Definitely in the first half of the dictionary, right? Okay. I think I'm going to, if anyone can hear me, I think I'm going to stop here and wait for the break. After the break, we'll continue from brute force algorithm, and then we'll just take it from there and wind down on software development and its application. I do not know if my colleague is still on the call, but we're definitely going to return by 12:30. All right.
Okay. Thank you, Mr. Jonathan. So, we will be going on a 30 minutes break. By 12:30, we have to be back on the call. So just take a short break, take a snap. Please don't take a nap. You can take more, you can sleep, you could sleep more than 30 minutes, but just kidding. We'll be back by 12:30. And while we're on break, the attendance is being posted. Please make sure to fill up the attendance. And if you're not on the Telegram group, please endeavor to do that. The link is in the chat room. Thank you. Security class resume by 1:30 and will last till 2:30. So let's all brace up as we continue the class. Mr. Jonathan, are you there with us? Mr. Jonathan?
Yes, I'm here. Good afternoon.
Oh, okay, good afternoon. Please, you can continue with the class. Thank you.
All right. Good afternoon, everyone. Welcome back. I trust the break was refreshing. Okay, let me just quickly share my screen so that we proceed immediately. Okay. All right. We were to proceed from brute force algorithms. Okay, we were to proceed from brute force algorithms. Now, brute force algorithms exist for every combinatorial problem, but they're not typically used because of runtime issues. To systematically enumerate all potential solutions, a brute force algorithm must generate every possible combination of the input data. For example, if a credit card number has 16 digits and each digit can have any value between 0 and 9, then there are 10 raised to the power of 16 potential credit card numbers to enumerate. Now, the combinatorial explosion is the exponential number of solutions to a combined problem. Brute force algorithms unusable in practice. Now, despite continual improvements to how quickly computers can execute programs, exponential time brute force algorithms are impractical except for very small problem input data. Examples of brute force algorithms would be trying to crack passwords, which in very most cases are illegal, except in the event whereby you are a certified ethical hacker who is, in that case, testing for the security of the systems of your organization, as the case may be. Other than that, brute force hacking, very much illegal, and it is banned during jail time in many climes. Now, moving on to greedy algorithms. A greedy algorithm solves a combinatorial problem by repeatedly applying a simple rule to select the next element to include in the solution. Now, unlike brute force algorithms that have combinatorial problems solve combinatorial problems rather by generating all potential solutions, greedy algorithms instead focus on generating one solution. These algorithms are greedy because they select the next element to include based on the immediate benefit. For example, a greedy interval scheduling algorithm might choose to work on the task that takes the least amount of time to complete. In other words, the cheapest way to mark one task is completed. All right? Just kindly give me a second. Just 1 second. All right. If the tasks are scheduled in advance and we are to work only one task at a time, choosing the task that takes the least amount of time to complete might prevent us from completing the longer task that just so happens to overlap in time. The greedy algorithm computes the shortest task to get the best result, the most optimal result using the data set it has at hand. It finds a solution, but not the optimal solution, not necessarily the optimal solution all the time. The majority of greedy algorithms do not always compute the best solution, but there are also certain scenarios in which cleverly crafted greedy algorithms guarantee finding optimal solutions. All right, the problem they solve are formulated to ensure that the greedy algorithm never makes a mistake when repeatedly applying the simple rule to select the next element. Consider the municipal broadband planning problem, more formally, the minimum spanning tree problem of finding a lowest cost way to connect all points. Again, vertices are points, to connect all points in a connected graph to each other. If we want to minimize the sum of the selected weights, one idea is to repeatedly select the next edge connections between vertices, which is the lines between points, with the lowest weight, so long as it extends to reach the network. And so it's like finding a shortcut. It's like taking the shortest route to find a solution, which is not necessarily the optimal case most of the time. Now, computer scientists have designed algorithms that repeatedly apply this simple rule to find an optimal solution, optimal minimum spanning tree. We have the Kruskal's algorithm, a greedy algorithm which sorts the list of edges in the graph by weight. Prime's algorithm, a greedy algorithm that maintains a priority queue of vertices in the graph ordered by connecting lines. And for most problems, greedy algorithms will not produce the best solution. Instead, algorithm designers typically turn to another algorithmic paradigm called dynamic programming. Still, greedy algorithms provide a useful baseline starting point for understanding problems and designing baseline algorithms for generating potential solutions. Now, the reduction algorithms. Algorithm designers spend much of their time modeling problems by selecting and adapting relevant data structures and algorithms to represent the problem and its solution in a computer program. This process of modeling often involves modifying an algorithm design pattern so that it can be applied to the problem. But there's also a different approach to algorithm design that solves problems by changing the input data and output data to fit a pre-existing problem. Rather than solve the problem directly, a reduction algorithm solves problems by transforming them into other problems. Now, transform the input data so that it is acceptable by an algorithm meant for another problem. Apply the algorithm meant for the other problem on the processed data. Transform the output of the algorithm meant for the other problem so that it matches the expected output of the original problem. I'm just going to run through these parts. Kindly give me another. Okay. Okay. I'm here. I'm here. All right. Okay, so I want to properly see if I can explain this reduction algorithm to you. Now, it transforms one problem into another. An example is solving a math problem by converting units. So if you need to find the distance a car travels, for example, in 2 hours at 60 miles per hour, but only know how to, for example, calculate the distance in kilometers, you first have to convert the miles that the car is traveling at using an algorithm, definitely, and then solve the problem finally. And so that's a reduction algorithm solution. And so if it's applying to a system or a software, a program, computer, as the case may be, right? The program is, or rather the software or system is programmed to be able to relate a bigger or simplify big tasks that are too complex per se for it to solve, simplify it, break it down to a point where it can understand, and then create a solution from that breaking point where it has reduced the problem to. And so that's basically it for reduction algorithms. Sample algorithms by problems. Now, earlier, we introduced several computing problems like searching for a target value in a list or implementing, if we remember what we discussed earlier about searching for elements or variables in a data set, in a sequential data set, otherwise called a list, or implementing an abstract data type such as lists, sets, maps, priority queues, and graphs. Now, although every computational problem is unique, these types of problems often share significant similarities with other problems. Now, computer scientists have identified many canonical problems that represent these common problem templates. Now, although each of these canonical problems may have many algorithmic solutions, computer scientists have also identified canonical algorithms for solving these problems. In this session, we will introduce canonical problems and survey canonical algorithms for each problem. Now, the data structure problems are not only useful for implementing data structures, but also a fundamental algorithm design patterns for organizing data to enable efficient solutions to almost every other computing problem. If we remember what we discussed earlier today and last week, you can only optimize your data if it is structured properly, if it is arranged properly, if it is optimized properly for space, which is the storage capacity, data storage capacity, as well as time, which includes the processing time for processing the inputs or the data sets, as the case may be, as well as processing what your output variable what you want to achieve with your output variable in an efficient manner, right? Such a way that it's optimal for both the end consumer as well as your business by extension. Now, searching is the problem of retrieving a target element from a collection of elements or a data set, as the case may be. Searching in a linear data structure, such as an array list, can be done using either sequential search or binary search. We've looked at this in detail. Sequential search being searching through list, array list, using the indexes in the list, or sequential search algorithm is a searching algorithm that sequentially checks the collection element by element for the target variable. The runtime for sequential search is ON, or N being the number of elements in the list. It's constant, and in some cases can be linear. Linear in the sense that it increases with direct proportion to the increase or decrease of the number of elements or variables in your data set. Now, a binary search algorithm recursively narrows down the possible locations for the target in the sorted list. As we've repeatedly mentioned both last week and today, binary search algorithm only works with sorted data sets. Where the data set is ordered in an ascending or descending order, as the case may be. Now, by comparing the target to the middle element of the range, we can rule out half of the elements in the range. In a dictionary setting, if you are dividing the dictionary into half, you find A in the first half, you find Z or Z, as the case may be, in the last half of the dictionary. And you find either M or N, the 13th letter in the alphabet, at the middle, definitely. So we've looked at all this both last week and this week. Sorting is the problem of rearranging elements into logical order, again, descending or ascending, typically from least valued, smallest to the greatest valued, ascending. Sorting is a fundamental problem, not only because of the task that it directly solves, but also because it is a foundation for many other algorithms, such as the binary search algorithm or the Kruskal's algorithm for the minimum spanning tree problem. Again, we looked at all this practically using Python Jupyter notebooks last week. So a merge sort algorithm recursively divides the data into sublists until sublists are one element long, which we know are sorted, and then merges the adjacent sorted sublist to eventually return the sorted list. And so the merge operation combines two sorted sublists to produce a new, larger sorted sublist containing all the elements in the sorted order, right? And so you have, for example, a scattered data set, right? And you want an algorithm that is able to go through it and get detail or an output variable, an output target from your data set. One way to do it is to break the algorithm down, sort the sublist of the data set from descending to ascending order, or from least value to the greatest value, and then go through the data set in question, bring them back together in an orderly manner. And so you have, for example, if you have a data set, we went through all that last week. I wouldn't want to go through it practically again. Just still a merge sort algorithm recursively divides the data into sublists until sublists are one element long, which are known
which we know as sorted, and then merges the adjacent sorted sublist to eventually return the sorted list. Now, the merge operations combine two sorted sublists to produce a new, larger sorted sublist containing all the elements in the order. All right. Now, a heap sort algorithm adds all elements to a binary heap priority queue, adds all elements in a binary heap priority queue data structure using the comparison operation to determine a priority value, and returns the sorted list by repeatedly removing from the priority queue element by element. And so the runtime for heap sort is just kind of give me a second, please. Just 1 second. All right, so I think I would revisit the runtime for the heap sort algorithm. Now, many comparison sorting algorithms share the same runtime, bound with n being the number of elements within the data set. Now, computer scientists have shown that with a combinatorial proof that in the worst case, a comparison sorting algorithm cannot do better than the runtime for heap sort algorithm. Now, it is impossible to design a worst-case runtime comparison sorting algorithm. In fact, a commonly used version of heap sort is to first build a binary heap. First, arrange the input numbers in an array, then repeatedly call a function to the original array into a binary heap. One can show that the runtime or running time of this part is linear in n, again, where n is the number of variables in the data set, which is why this is faster than constructing a heap by adding numbers 1 by 1. Right? Okay. Another type of sorting problem that is not restricted to pairwise comparisons is known as count sorting, or sorting a list of elements by organizing elements into categories and rearranging the categories into a logical order. For example, the problem of sorting a deck of cards can be seen as a count sorting problem if we put the cards into numeric stacks and then rearrange the stacks by changing the assumptions. And now this is a real world or real life example of this algorithm, as the case may be. By changing the assumptions of the problem, count sorting algorithms can run in a constant time, really 0n being a constant time where the time doesn't change despite the size of the data set in question, by first assigning each element to its respective category and then unpacking each category so that elements appear in sorted order. All right, so I'll quickly move over to hashing. Now, hashing is the problem of designing efficient algorithms which map each object to an integer. Again, if you remember, which map each object to an integer so that most objects will be assigned distinct integers. Although hashing algorithms are often specific to each data type, there exist some general approaches for designing hashing algorithms. The hash value of a simple data type, such as an integer, can just be the value of the integer itself. Now, the hash value of a string text can be some mathematical combination of numerical values of each character in the string. And I'm going to just quickly break that down. Now, hashing is the same as assigning a unique ID number to every object so that we can quickly find them later. if you remember what I spoke about indexing, it's almost like indexing within a list data type, right? Or a linear data set, an array list, right? So if I want to find, what's the word now? If you ask me, if you want to find my location, right? And you ask me, how do I get to see you next weekend? My possible answer to you, if I'm not giving you a phone contact or an email contact, my possible answer to you would be that I dwell at maybe number 1, Fine Street, Ikorodu, Lagos, right? That's a possible answer. Now, the allocation of that ID number is what's called a hashing, right? Or a hashing algorithm, right? Hashing, rather, not a hashing. It's called hashing, right? You want to be able to identify each element within a data set with a unique ID number so that it can be found at any point in time when you are searching for the element in the data set. Now, hashing has a variety of applications spanning computer systems, database systems, computer security, and searching algorithms. Again, if you're looking for elements or variables within a data set. For example, hashing algorithms are often used designing secure systems for protecting stored passwords, even after a security breach occurs. In the context of data structure problems, hashing offers a different approach than binary search. Instead of relying on pairwise comparisons to narrow down the expected location of an element in a sorted list in logarithmic time, hashing such algorithms can instead directly index an element by hash value in constant time. Again, taking us back to integer indexing or data element indexing, right? In the event where you need to locate the element or variable in the data set. Now we have things like the graph problems. Now, while data structure problems focus primarily on storage and retrieval of elements in a collection or a data set, graph problems include a wide variety of computing problems involving the graph data structure. Now, unlike data structures, graphs include not only elements or points, but also relationships between elements, which are the lines that connect the points within the graphs. Graph problems often ask algorithm designers to explore the graph in order to answer questions about elements and the relationship between those elements. Again, vivid examples of this. Okay, so okay, let me not use that example. I wanted to give an example right now, but that would be a map problem, a mapping problem. And that will not be interchangeable with the graph problem in this context. So I think I would stay put with that for now. We also have the traversal problem, which is a problem of exploring all the points in a graph. Now, graph data structures differ from tree data structures in that there's no explicit root node, or no beginning, rather, no beginning to the movement, and the lines cannot connect back to other parts of the graph. Now, in general, there's no guarantee of hierarchy or well, hierarchy, I believe that's self-explanatory, but in the event where it's not self-explanatory, there's no guarantee of order, ascending or descending order in a graph, right? So graph traversal algorithms such as depth first search and breadth first search begin at an arbitrary start point and explore outwards from the start point while keeping track of a set of explored points. The depth first search hello.
Yes, we're with you, Mr. Jonathan.
All right. All right. Let me just quickly go back to my slide. All right. Now, the depth first search is a graph traversal algorithm that recursively explores each neighbor, continuing as far possible along each subproblem, which is otherwise called depth first. Now, explored points are added to a global set to ensure that the algorithm only explores each point once. The runtime of depth first search is constant, basically, where V means the number of points and E means the number of lines that connects those points together. The 0 here just definitely means constant, means there's no change in the runtime for depth first search. That's simply the meaning of the 0 there. And so you have examples given here in the images, which definitely you will be able to go through with the material. Now, a breadth first search repeatedly explores, iteratively simply means repeatedly. And so it repeatedly explores each neighbor, expanding the search level by level, breadth first. Now, explored points are also added to a global set to ensure that the algorithm explores each point once and in the correct level order. The runtime of breadth first search is also constant, where V means the number of points or vertices, and E, which means the number of edges, means also the number of lines, where edges means lines. Now, graph traversal algorithms are the foundational algorithm design patterns for most graph processing algorithms. Many algorithms require some amount of exploration, and that exploration typically starts at some vertex or point and continues processing each reachable point at most once. Now, a reachable point can be reached if a path or sequence of edges from the start point exists. As opposed to depth first search, breadth first search has the benefit of exploring points closer to the start before exploring points further from the start. Now, you'd have the material and you'd be able to practicalize and work with all this in more detail. Minimum spanning trees is a problem of finding a lowest cost way to connect all the points to each other, where the cost is the sum of the selected line weights, right? And so the two canonical greedy algorithms for finding a minimum spanning tree in a graph are Kruskal's algorithm and Prime's algorithm. Both algorithms repeatedly apply the rule of selecting the lowest weight line to an unconnected path of the graph. Again, the example whereby I gave earlier in the day, if I'm trying to find the fastest and most cost-effective route from where I reside in Lagos to Ibadan. Let's say I'm trying to maximize my fuel consumption, or I'm trying to save money, or save time rather. I'm trying to save time, I'm trying to save fuel, right? And I am new to Nigeria, right? And I say, okay, I want to cut down my expenses and cut down the time. I'm in a hurry. What's the fastest route to, let me not even use Ibadan. What's the fastest route from Lagos to Benin, right? And, or Lagos to Benin might even be, that's just an example, you know, fastest route from one point to another, right? And then I go through the map and I ask the map, for the map to carry out such calculation, it uses what's called minimum spanning trees algorithm, right? it goes through what's called a minimum spanning trees problem and makes use of either the cross-cause algorithm or the primes algorithm, as the case may be. The cross-cause algorithm begins by considering each point as an independent island, and the goal of the algorithm is to repeatedly connect islands or each point by selecting the lowest cost lines, the lowest cost route, in this case, that connects each location to the other. Now, a specialized data structure called disjoint sets is typically used to keep track of the independent point on the graph, within the graph. The runtime for Kruskal's algorithm is also constant, where E is the number of lines that connects the locations or points within the graph, as the case may be. Again, you'd have the material and you'd be able to go through it in a more practical sense. Now, Prime's algorithm shows a minimum spanning tree, grows a minimum spanning tree rather, one edge at a time, lowest width line to an unexplored point. The runtime for Prime's algorithm is also constant with respect to V, where V is the number of points and E is the number of lines. The output, now we've moved over to shortest path. Now, the output of a shortest path algorithm is a shortest path tree, the lowest cost way to get from one point to every other point in a graph. The unweighted shortest path is the problem of finding the shortest path in terms of the number of lines, or in a much more practical sense, the number of routes to each point on the graph. Given a start point, breadth-first search can compute the unweighted shortest path tree from the start point to every other reachable point in the graph by maintaining a map data structure of the path used to reach each point. Again, back to the practical example, if you're asking Google to direct you to a point using its map and finding the shortest possible route or shortest possible path, again, it makes use or utilizes the shortest path algorithm in this context. The weighted shortest path, a weighted shortest path is the problem of finding the shortest path in terms of the sum of the line weights or the route weights in a much more practical sense. Now, earlier we introduced Prime's algorithm, a minimum spanning tree algorithm that maintains priority queue of edges or lines in the graph ordered by weight and repeatedly selects the lowest cost edge or line to an unconnected path of the graph. Again, we have practical examples for it here. All right, so now we move on to Dijkstra's algorithm. The Dijkstra's algorithm maintains a priority queue of points in the graph ordered by distance from one start and repeatedly selects the next shortest path to an unconnected path of the graph. Now, the Dijkstra's algorithm is almost identical to the Prime's algorithm, except processing shortest paths rather than individual lines or routes. Now, the Dijkstra's algorithm grows a shortest path tree, one shortest path at a time, by selecting the next shortest path to an unexplored vertex or point on the graph or the map. The runtime for the Dijkstra's algorithm is constant. And so part of the things we want to note, aside from the whole description of the algorithm, part of the key things we want to note is when do we make use of this algorithm or these various or multiple algorithms in question? What are the run times for the various algorithms? And why do we need to, why do these run times, this variety of run times apply to the variety of problems we want to solve, right? And so each runtime is unique in solving its own challenge. And also, okay, so it's unique, yes, in solving its own challenge, right? And so we need to find what is the problem at hand. Again, maximizing time. So what is the shortest route or path? Again, depending on the distribution of the locations, we would also have to look at, given the fact that all these various graphical algorithms are all constant, hence, given the distribution of the location, how does it apply to each algorithm? Because we find that each of the graphical algorithms that we've all looked at, whether it be the Dijkstra's algorithm, the weighted shortest path algorithm, the primes algorithm, and so on and so forth, each have the unique ways in which they address distribution of locations, right? In which they address routing, distribution, routing in movement or in, yes, in movement with respect to the difference in the distribution of locations or points on the graph. And so again, the key things we need to take into consideration when we're looking at what's the best choice algorithm to use for a graph problem is the time and the distribution of the location or points on the graph or the map. And so the distribution of location or points on the graph or the map would enable us to be able to say, okay, what's the best route between these locations, and what's the weighted distribution of these routes, right? And it helps us arrive at what is the optimal solution to creating the shortest movement between these points on the graph. And we can thus program a system or software or AI, as the case may be, to utilize the algorithm in question. Now, we move over to models of computation. Computers include basic algorithms for solving problems like adding, subtracting, or comparing two numbers. Again, those are referred to as operations. Computers, owing to their roots in calculators, are optimized to solve these problems. These basic algorithms are constant time operations. Now, what programming offers is the ability to define our own algorithms that can be used to solve more complex problems such as searching, sorting, and hashing, all of which we've discussed both today and last week, Saturday. Now, unfortunately, these programmed algorithms are not as fast as basic operations. We have even seen certain problems deal with a combinatorial explosion in the number of potential solutions. For many of these problems, the best known algorithms do not do much better than brute force, which takes exponential time, rather. Now, in the best picture, computer science engages the central question of how humans can encode intelligence. Our own discussion of algorithm design grounded the activity in problem modeling. Again, taking back the question, or taking us back rather to what we discussed earlier today, the task of data modeling for seamless programming. Again, relevance of the variable in question, and then compressing too much information or too much, again, too much irrelevant information into tiny bits of code, what again will become relevant for the computer to remember and relevant for the computer to achieve the desired output that it wants. So the process of encoding a complex real-world phenomenon or problem in an abstract or simple form. How is problem modeling constrained by the model of computation or the rules of the underlying computer that executes an algorithm? Why are certain problems challenging for computers to execute? Now, the combinatorial explosion poses a problem for computer algorithms because our model of computation assumes computers only have a single thread of execution and only execute one basic operation on each step. Now, if we overturn some part of this assumption, either by creating computers with multiple processors or by creating more sophisticated operations, e.g. quantum computers and quantum operations, then it might be possible to deal with combinatorial explosions. Almost all of today's computer hardwares, ranging from massive supercomputers to handheld smartphones, rely at least to some degree on the expanding of the model of computation to compute solutions to problems more efficiently. Even so, much of today's computer hardware still relies on the same fundamental programming assumptions that they are variables to represent data and arithmetic or logical operations. Now, onto Turing machines. In the 19th century, which we call the 1800s, Charles Babbage imagined a mechanical machine, the analytical engine, that could automatically calculate mathematical formulas. Now, Ada Lovelace then proposed that the analytical engine could solve more general algorithms by using loops to repeat processes and variables to represent data. Now, Lovelace's vision of algorithms represented a synthesis between human intuition and mathematical reasoning. In the 20th century, or the mid-1900s, Lovelace's ideas inspired Alan Turing to imagine a more general notion of algorithms and machines that could run those algorithms. A Turing machine is an abstract model of computation for executing any computer algorithm. A Turing machine describes computers in terms of three key ideas. Number one, being a memory bank for storing data. Number two, being an instruction table where each instruction can either store a value to the memory bank or retrieve a value from the memory bank or perform a basic operation on a value and set which instruction should be executed next by modifying the program counter. And then number three, according to Turing machines, a program counter that keeps track of the current instruction in the instruction table. Now, a Turing machine executes a computer algorithm by following each instruction specified by the program counter. An algorithm can use these basic operations to compute the sum of 1 and 1. Number one, store the value 1 to address A in the memory bank. Number two, store the value 1 to address B in the memory bank. Number three, add the values at addresses A and B and then store the result at address A. Now, what makes computers useful is not just the fact that they can calculate numbers, but that it can encode logic in the instructions. And so instead of just computing the sums of 1 and 1, this program continues adding 1 to a growing sum stored at address A. Store the value 1 to address A in the memory bank. Store the value 1 to address B in the memory bank. And add the value at address A and B and then store the result at address A. And then number 4, set the program counter to execute step 3 next. Now, finally, on Turing machines, the Turing machine abstract model of computation assumes a single thread of execution following each instruction in an algorithm. Although today's computers are much more efficient than the first computers that realized the Turing machine, most computers still rely on the same fundamental assumption about how to execute algorithms. That is the constant time sequential search algorithm. Now, though it might execute 1,000 times faster on today's computers, it still grows linearly with respect to the size of the input. Now we move over very quickly to complexity classes. Now, one subfield of computer science as a computer scientist is the theoretical computer science, which studies models of computation, the application to algorithms, complexity of problems. The complexity of a problem is the complexity in terms of time or memory resources required, again, which we've looked at earlier today. We spoke about finding data storage capacity, and so you would want to create the best fairly utilizes your data storage capacity and then also creates solutions in a fair time for both the end user or consumer, as the case may be, and with extension or by extension, rather, your business at the end of the day. Now, the complexity of a problem in terms of time, in terms of memory resource required, of the most efficient algorithms for solving the problem, theoretical computer scientists are interested in understanding the difficulty of a problem in terms of time complexity, number 1, space complexity, number 2, and some other complexity measures as well. And those other complexity measures involve measures such as where you're trying to route multiple locations and you're trying to find, okay, what is the link between, what's the shortest link between point A and point B, given unequal distributions of the locations in question. Now, that's just an example of some other complex or complexity measures as far as computer theoretical science is concerned. Now, in this chapter, we are focused on solving problems known to have polynomial time algorithms. Now, searching, sorting, hashing, traversal, minimum spanning trees, or shortest path are all examples of problems in the polynomial time complexity class, because they are all problems that have runtimes with a polynomial expression, such as constant 1 or constant depending on the number or the position of the element in the data set. In general, these problems are considered tractable because computers can solve them in a reasonable amount of time. But there are many problems that are considered much more understandable complex because they do not have efficient or polynomial time algorithms, right? The non-deterministic polynomial time complexity class refers to all problems that can be solved in polynomial time by a non-deterministic algorithm. Now, a non-deterministic algorithm is a special kind of Turing machine, which at each step can no deterministically choose which instruction to execute and is considered to successfully find a solution if any combination of these non-deterministic choices eventually lead to a correct solution. Now, in other words, in contrast to a deterministic algorithm, such as greedy algorithm, which must repeatedly apply a simple rule to deterministically select the next element in a solution, a non-deterministic algorithm is able to simultaneously explore all the possible choices. We're rounding off, so I will just explain that in very simple terminology, right? Just kindly give me a second. Okay, so in very simple terminology, just to round off, the key difference between a polynomial time algorithm and a non-polynomial time algorithm is that the initial one, which is the polynomial time algorithm, solves problems efficiently for larger inputs. And so if you are looking at, for example, very large-scale data sets, in the event where you are working or creating a data model rather for a large target audience with variety of variables, right? That will include examples, real-world examples for that would be studying patterns in aging, right? Studying patterns in aging, it varies from individual to individual, and even within one individual, it varies from time to time. And so you're going to be working with exceedingly large data sets for such a project, as the case may be. You're going to have to make use of the polynomial time algorithm, which solves efficiently for larger inputs. Examples of those would be things like the we've looked at earlier. Shortest path algorithm is actually graph, but in this time, or at this point rather, I'm discussing at this point I'm discussing okay, I'm pretty sure you'll be able to see examples on that. Nothing's come to my mind right now. Let me just quickly see if I can just quickly make a quick research on that. A very few seconds. But before I make a research on that, non-polynomial time definitely takes way too long to solve as input grows. And so in the event where you are working with exceedingly large data sets, example, patterns in aging, patterns in medical changes as aging occurs, non-polynomial time algorithm definitely is non-suitable for your operations, your data operations, as the case may be. I would round off on that here for now, and I would leave the floor open to the moderator for questions as well as round off on this session as we prepare for OWASP Top 10. Yes, thank you, and thank you once again. Hello.
All right. Thank you, Mr. Jonathan. While we're waiting to start the OWASP, please take a minute to fill in the attendance. The link is in the chat room. Please take a minute to fill the attendance. And like I said before, if you're not on the Telegram group, please try to join. The materials, the video, and every other thing will only be posted on the Telegram group. So please do well to join us on Telegram. while we take some minutes for us to start the OWASP session. Thank you.